Hello guys, today what we're going to do is we're going to spend a little bit of time going over some graphs to interpret the graphs and to transpose one graph onto another graph. So I'm going to go ahead and switch to my document cam, and we're going to work through these for just a little while in preparation for some practice and a quiz that you guys are going to do. All right, so I'm going to go ahead and switch over to document cam here. And as you can see, the instructions on here say, or asked us to convert the following displacement versus time graphs into velocity versus time graphs. So by looking at these different graphs, this should allow us to better understand the relationship between displacement and velocity. Now on their graph, they put down a D right here. I'm going to change this. We usually use X for displacement, or for position, so displacement would be the change in X. And this graph, of course, in the bottom is time along this axis. And this, of course, will go for all of these. Like so. All right, that's going to make it look a little bit more like some of the graphs that we've talked about. Down here, we've got velocity on the y and time on the x. So again, these will be v and t, v and t, v and t. Okay. So we're going to focus just on this first graph right here, and we'll kind of move one after the other. Okay. So if I look at this, remembering that this is position as measured in meters, okay? I would ask you, my first thing that I would ask you, and anytime I would look at a graph like this, the first thing I want to know is, what's this, is there motion here? And if there is, what kind of motion is it? Okay, so I would ask you first, just looking at this graph and this graph alone, is there motion shown in this graph? I want you to think about that for a second. Now what I would say, if I looked at this, is I'm noticing that my position here is changing. At time 0, I'm at 0 meters, but at time 1 second, I'm at 1 meter. Okay, so I've moved from 0 to 1 meter away after 1 second. After 2 seconds, I'm 2 meters away from where I started. After 3 seconds, I'm 3 meters away. Okay, so 3 meters away. After 4 seconds, I'm 4 meters away, and so on and so forth. So am I moving? Yes, I can see clearly that my position is changing here. So the fact that I have changing motion means I have some kind of motion occurring. Okay, my changing position means I have some kind of motion occurring. The question is what kind? And we really only have 2 types. If you have motion, you're either going to be moving with constant velocity or with acceleration. Now, if you notice what's happening here, every second that passed, okay, each second that passed, I moved 1 meter. So during the first second, I moved up 1 meter. During the second, I moved another meter. During the third, I moved another meter, so on and so forth. So what you notice is this straight line is always going to represent constant motion, or constant velocity, let's say. All right, anytime you see a graph of x versus t, and then there's a straight line on it that is not horizontal, all right, a line that's at an angle, it's not horizontal, but it is a straight line, it's going to be constant velocity. So if I think about how I'm going to transfer that down here to the velocity versus time, and remember, if this is velocity, it would be meters over seconds. Time, of course, is going to be seconds. To figure out how I'm going to transfer that, if I have a constant velocity, what must be true is that the line on the velocity graph, if it's going to be constant, it has to be horizontal. All right? Because let's just remember, these are meters per second. If I look at this particular one, we can figure out what our velocity is we have a formula for this. We said that velocity is going to be delta x over delta t. So I can take any portion of this graph because the velocity is constant, I should get the same answer. So if I think about the entire line, all right, what was my delta x, my change in position? Well, I went from 0, and at the end of the line, I'm all the way up at 7 meters. So my delta x then is 7 meters. Okay, how long did that take? What was the time that occurred during that? Well, I would basically go all the way from 0 seconds to 7 seconds. That's the point at which I was at 7 meters. So this was 7 meters in 7 seconds. Well, if I simplify that velocity, what would it be? 7 divided by 7, it's simply 1. This would be positive 1 meter per second. Now notice that on the velocity graph, because my velocity is not changing, this is simply a horizontal line that's at 1 meter per second. So the whole time we were traveling 1 meter per second, as shown by this position versus time graph. So as we move on, we'll look at the second example here. Again, what I notice right off the bat is I've got 2 segments here. Now, one thing I want to draw your attention to first is the segment that goes from 2 seconds over to 7. So this line right here. Now, what do you notice about this line? Number one, it's a straight line. All right, it's a straight line, and it's horizontal. Now, what does that mean? Well, if you think about it, that means at 2 seconds, this object was at 6 meters. What was it at 3 seconds? Well, at 3, it was still at 6. At 4, it was still at 6. It was at 6 meters all the way to 7 seconds. That means it did not move at all during this period. So something you should notice, if you have a graph that has a horizontal line in it, all right, a horizontal line, that means that represents a period where whatever the object is at rest. All right, it is not moving here. I can tell because it stayed at 6 meters the whole time. It never deviated from that. So a horizontal straight line means you're at rest. A straight line, excuse me, a straight line that is at an angle like this one is constant velocity. So if I look at this here, this must be constant velocity. I'll just say velo. Okay. So I've got a period where I was moving with constant velocity. I know I was moving because my displacement changed. Each second, my displacement for 2 seconds, I was moving because my displacement changed. Okay. So you know what I'm going to do is when I convert this to a V versus T graph, I'm going to do these last from 2 seconds to 7 seconds. I'm going to do that first because I think it's easier. If I'm at rest here, what would my velocity be if I was at rest? Well, if I'm at rest, my velocity must be 0. I'm not moving. So I know that from 2 seconds all the way over to 7 seconds, my velocity must be 0. So I'm going to draw a line right along there to show 0 velocity during that period when I was at rest. Now, what happened before that? Well, from 0 seconds to 2 seconds, I clearly have some kind of velocity. I know it's constant because the line is nice and straight. So we're going to do this portion just like we did the other one, and we basically say that if my velocity is constant, I can determine what the velocity is by calculating the average velocity, which would simply be delta x over delta t. So what is my delta x for this period between 0 and 2 seconds? Well, during that time, I went from 0 meters. Remember, this is our meters on this axis. I went from 0 meters up to 6 meters. So what was my change in position if I went from 0 to 6? Well, it would simply be 6 meters. And what's my delta t? How long did that take to go from 0 to 6 meters? How long did it take? Well, here I'm looking along this axis, the time axis. And I can see that to get from here to here, it took 2 seconds. So I would say that my delta t is 2 seconds. Now, if I do the math, it's not hard. 6 divided by 2 is positive 3 meters per second. So what does that mean? That means between time 0 and time 2 seconds, so in that gap, I must have had a velocity of 3 meters per second. And so did that velocity change during that 2 seconds? The velocity change? No, it was constant, meaning it was 3 the whole time. So I'm going to draw a line right at 3 meters per second on my velocity graph. So during those first 2 seconds, I was moving at 3 meters per second. To finish this graph off, all I need to do is just connect the two. That's all you got to do. So that is my velocity versus time graph for this particular xt graph. Okay? They should start to get easier, hopefully. So hopefully you're kind of paying attention here. And as I'm going through these, you're listening to the description, you're kind of picking up some of the tricks. Okay? So one of the tricks I used here was this idea that if I have on the x versus t graph, if I have a horizontal line anywhere, that's a period that I'm at rest. So here I was at 6 meters and I stayed that way. Okay, I stayed that way. Now if I look at the next graph, I see the same thing. I see a horizontal section here. What must be true about this? If it's horizontal, that means I'm at 4 meters at second 4, second 5, second 6, and second 7. That whole time, I was at 4 meters. What's your motion going to look like? You must be at rest. You've got to be at rest. Okay? So I know right off the bat that here, if I'm at rest, I have no velocity for this velocity graph. So I can go right on down here. Doesn't matter where I was. The fact is, this isn't graphing where I'm at. This is graphing what my speed, my velocity is. And if I'm at rest, I know that my velocity then is 0. So from second 4 all the way to second 7, I know that this line is going to be right on the 0 axis. Okay, we can call it the x, I guess, if you want to. But it's basically my speed is going to be 0 that whole time. I know because my displacement here did not change. All right, let's go to this segment that's here. What would you say about the velocity here? Is it at rest? It can't be at rest because this, whatever this object is, it was experiencing a change as you went from here to 2 seconds later, from 2 seconds to 4 seconds. My position changed from 2 meters to 4 meters. So my position's different. I must have been moving. What did that motion look like? Well, the fact that it's a straight line tells me this is constant velocity again. So the question is, what is that constant velocity? We've already done this on the first two. To figure out what the constant velocity is, we just say that the velocity equals delta x over delta t. All right? So what was our delta x? From 2 seconds to 4 seconds, okay, that gap right there. How much did this displacement change? Well, I went from 2 to 4. So I had a 2 meter change in my position. And that 2 meter change in position occurred over what time interval? Well, I went from 2 seconds to 4 seconds. And so my change in time, my delta t, is 2 seconds. This is some pretty tough math. 2 meters divided by 2 seconds, that means it's 1 meter per second. So I know that my velocity during this period of time is 1 meter per second. Where would that be? Well, positive 1 meter per second is this line right here. So between 2 seconds and 4 seconds, I should have a line right there. That speed is 1 meter per second, so I'd have a line on the 1 meter per second line there. I can go ahead and connect this with that first segment by just drawing a line. Okay? So notice here, we realize this has some velocity. I know it's not 0 because it did change its displacement. We can figure out what that velocity is by just dividing delta x by delta t. All right? We're going to do that with this last segment here. Now, because it's a straight line and it's not horizontal, the fact that it's not horizontal means it's not at rest. It does have some velocity. So what would the velocity be? We're doing the same thing. All right, my average velocity for this segment is going to equal delta x over delta t. So what is my change in position? Well, I went from 6 down to 2. From 6 down to 2 during this space here. So what's that change? Well, if I go from 6 to 2, I must have taken away 4. It's basically 6 minus 2, or really we'd say 2 minus 6. Because it goes from 6 to 2, the change was negative 4 meters. All right, negative 4 meters. I went from 6 to 2, so my change was negative 4. How much time did that take? Well, the time it took is 2 seconds. So basically, the velocity along this line would simply be negative 4 divided by 2, or negative 2 meters per second. All right, so I can fill in this last gap here, these first 2 seconds. We were traveling at negative 2 meters per second. So all that means is my velocity will be down here. Now notice it doesn't change. The fact that this was a straight line meant it was constant at negative 2. So I'm just going to draw a segment here that's right at negative 2. And I finish that graph. Okay, this is what the v versus t graph for this is going to look like. One more, then we're going to switch and do some different looking graphs. Okay. Okay, I'm looking at this. Anything jump out at you? Well, what jumps out at me right off the bat, I'll get the easy parts done first. I've got a horizontal portion here where my displacement was at 1. From 6 seconds to 7 seconds, I was at 1 meter and I didn't move, which means during this last second of time, between 6 and 7 seconds, this object was at rest. Okay? It was at rest during that period. I know because it was at 1 meter the whole time. And if I'm moving, my displacement has to change. So in this case, it didn't change. We're at rest. That means my speed during that period of time, if I wasn't moving, my velocity must be 0. So I'm going to have a small segment here that's right along 0, the 0 axis, I guess we could say. Okay, this next one that we got here, straight line. Okay, straight line. Let me see if I can get that to focus. That's a little better. Okay, straight line at an angle. This is constant velocity. All right, and really, while we're at it, here's another straight line at some angle. This is a constant velocity too. So let's tackle this one first. We'll kind of work it backwards, but it really doesn't matter. You can do these in any order you want. What is this velocity? Well, I know whenever I want to calculate velocity, we're just going to say v equals delta x over delta t. So what's my delta x here? And remember, x is on this axis over here. So how far did we move when we went from here to here? Well, I'm starting at 7, and I'm ending at 1. So to go from 7 down to 1, that change is -6. All right? To go from 7 down to 1, my change that in the x that occurred, or delta x, is going to be -6. Okay? How about the time? What's my change in time? Well, my time went from 4 seconds. All right, we started that velocity at 4 and we ended at 6. That means my delta t is simply 2. If I do the math, what velocity did we get over here, you guys? Well, -6 divided by 2 is simply -3 meters per second. All right. This is really pretty simple once you get down to it. So don't let yourself get confused. Understand that these graphs, when they're at an angle, that means that you've got a velocity that's going to be the same, and it's not 0. Horizontal, your velocity is 0 every single time. If it's at some angle, that means you're going to have a velocity. It's not 0, but it is constant if it's a straight line. So we can go ahead and mark this in between time 4 and time 6. During this period of time, our velocity was -3. So I can go down here and find -3. It's right here on the graph. I'm going to go over between 4 and 6, and I'm going to write a horizontal line in between those two times, because I know that during that period of time the velocity was at -3 meters per second. And so if I write any line along here, that means it stayed at -3 meters per second the whole time. Again, I can join with a line in between the two. Okay, now again, why was this negative? Because my change that occurred here was negative. The change in the displacement went from 7 to 1. That's a -6 change. Okay. All right, let's do this last one. Now, while this one was negative, notice the slope on this compared to this. This has an opposite slope of this, which means if this is negative, this one's got to be positive. How positive? We're doing the same thing. V equals delta x over delta t. So what's my delta x for this one? And remember, you're going to measure that here. What do you get? Well, I went 1, 2. I went +2 meters. You know what? I'm going to write this down here. V equals +2 meters divided by, how long did it take? What's the delta t here for this? Well, we started at 0, went 1, 2, 3, 4 seconds. So it took 4 seconds to go from 5 meters to 7 meters. So I'll say 4 seconds right there. Now, we can do this math. What's 2 divided by 4? Well, I can simplify that and simply say 1/2, okay? 1/2 meter per second. So where would that be here? Well, I can see it's positive, so it's above 0, and it would be halfway between 0 and 1. So I'm going to put a dot right there. I'm going to put another dot over here at 4, because 4 seconds is when that velocity changed right there. And I could just draw a line between, ooh, horrible line. Draw a line between these 2 points and connect it with the bottom one. And we have a V versus T graph that matches this one here. Okay. All right. So we're going to do another set here. We'll just keep on going. All right. So here's another set. Now, what do you notice about this one? How's this different from the previous set? Again, that's not D. This is X. And we're going to say T, XT, 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 And these are VT, VT, VT. Now, if you notice, the big difference between these and the last is that instead of knowing what the displacement versus time one is and solving for the velocity versus time, we're doing it backwards. All right, we're doing it backwards. Now, they are giving us where we start. So the dots here are showing where the object is going to start. So if I look at this first one, again, we're working backwards here. This is telling me that I have a velocity that is -1 meter per second. Okay, that's what these units are. -1 meter per second, and it doesn't change. It's always that. It's always that. So what I would say on this first one is I've got a velocity, a constant velocity of -1 meter per second. And so that means that for each 1 second that I move over, I lose 1 meter, -1. So over 1 second, down 1 second. I go 1 more second and I lose another. 1 more second and I lose another meter, and so on and so forth, all the way until I get right here. So if you look at this, this is pretty straightforward. This is simply a line that goes downward like so. Notice though, as soon as we realized that this was negative, we knew it had to go this direction, not this direction. Right? Negative, it always slopes downward as you go to the right if it's negative. That's your first one. Okay? All right, so let's go back to this. Now, what do you notice on the second example? What do you guys notice about that line right there? It's horizontal, which means your velocity is constant, but even more importantly, it's right at 0. So what's the object doing right during this first 2 seconds here? And these are seconds. What's the object doing here if your velocity is 0? Well, it must be at rest. All right, if it's at 0 velocity, you must be at rest. So what's happening to its position over time if it's at rest? Well, if it's at rest, its position won't change. So that means for those first 2 seconds, that position is going to stay right at 1 meter. It will not change. Okay? Then what happens at 2 seconds? Well, suddenly at 2 seconds, you're going to move into a nice horizontal line here, means constant velocity. What is the constant velocity? Well, you're going to have a constant velocity or an average velocity that is going to sit right at 3 meters per second. Okay? And how long is it going to do that? Well, that velocity is going to be at 3 meters per second for 2 more seconds, from 2 until 4. So let's think about that for a minute. If I have a velocity that is 3 meters each second, what about the position here? When we move up to the position versus time, is it going to stay right at 1 if I now have a velocity 3? It can't. I'm going to have to see a change in position because I now have a velocity. I'm moving. Okay? Now again, this velocity is 3 meters per second, and it's going to occur for 2 seconds. Right? This is 2 seconds you're representing here. Go from 2 to 4. So between 2 and 4 here, I'm going to see a change towards the positive direction, or upward, not downward. Okay? How fast? At 3 meters per second. So each second, I'm going to go up 1, 2, 3 meters in 1 second. 1, 2, 3 meters in 1 second. So that middle line, I can simply draw from here to there. Okay? So what happens here? That's a horizontal line, right? That's a horizontal line right at 0. So we're talking, remember, we're talking velocity here, not position. So if my velocity is 0 during this period of time, what's going to happen to position? If you have no velocity, your position will not change. So when I look at this, this is simply going to be a line that stays right where it is, right at 7 meters, all the way out to 7 seconds, because I have no velocity during this period I can't have a change in my position. This is the graph that's going to go with this velocity graph. All right, on we go. Again, I see a bunch of horizontal lines. What this means here is I've got constant velocities at every one of these steps. And the middle step is probably one of the easiest ones because that line right there between 3 and 4 seconds happens to be horizontal. That means you have no velocity. All right? You have no velocity during that period of time because it's right at 0. And that would mean that I'd be stuck in that position, wherever it is. Now, our problem is we don't know what it is yet because this is where we're starting. And we had a velocity here. Remember, this is going to be constant velocity. And it's not 0, it's positive 2. So I know that my velocity here in this segment is going to be 2 meters per second. And it's positive 2 meters per second. So starting off at my starting position, I'm going to have a velocity that's going to change, or that's going to change this position by 2 meters each second in time. All right, that velocity is 2 meters per second. So in 1 second, there's 1 right there. At going from 0 to 1, my position is going to change by 2 meters. Okay, so I go over 1 second and up 2 meters. I'll make a little dot right there. Now realize this is going to go on until we get to 3 seconds. So after 1 second, we've moved 2 meters. After another second, we move 2 more meters. Again, we're maintaining this velocity right here. 1 more second goes by, and I go up another 2 meters. So it's going to go all the way up to there. So this would be 1, 2, 3 seconds, just like we're showing here. All right, so for 3 seconds, we traveled at 2 meters per second, 2 meters per second, 2 meters per second. Okay, then what happened? We got this period where we know we're at rest, okay? We know that we are at rest during that period of time. What's that going to do to our displacement? We're not going to have any during this period of time. It's going to stay right where it is between 3 and 4 seconds. So this will just be a horizontal line right here. Guess I can go ahead and fill this in. Oh, that was horrible. It should be straight, even though it doesn't look like it. Okay. All right, let's look at the last one here. What's our velocity here? I know it's not 0. I actually know that it's negative. So I already know this line is going to be sloping downward. How much is it going to slope? Well, your velocity during this period is simply going to be negative 2 meters per second. So once again, each second, it's going to change by negative 2 meters. So in going from 4 to 5, that's 1 second time, I'm going to drop by 2 meters. Okay? 1 more second's time, I'm going to drop 2 more meters. 1 more second's time, I'm going to drop 2 more meters. Okay? So again, these make up a straight line, and I can fill that in. That's what my graph is going to look like for this velocity graph. One more, guys. So how are we starting here? Well, this velocity that they're showing right here is going to be negative 1 meter per second. Okay? That's 1 meter, negative 1 meter per second. So that means that each second's time for what? 4 seconds. Each second that passes, I'm going to drop by 1 meter. So we go 1 second passes, drop 1 meter. 1 more second passes, drop another meter. 1 more second passes, drop another meter. And that's going to go until 4. So we got 1 more. Down 1, over 1. Okay, so for 4 seconds, each time a second passed, we dropped a meter. Second pass, drop a meter. Second pass, dropped a meter. Second pass, drop a meter for 4 seconds. Now this is just a big game of connect the dots, you guys. All right, that's what my first line is going to look like. Then what happened? All of a sudden, I went from having a velocity that's negative 1 meter per second to having a velocity here that is going to be equal to 4 meters per second. 4 meters per second. So each second, only 1 second passed. So in going from 4 seconds to 5 seconds, all of a sudden now my velocity changed so that I've got 4 meters for that 1 second. So for the 1 second's time, it's going to climb 1, 2, 3, 4 meters. All right? That would be 4 meters of displacement in 1 second. And I'll connect those two. Okay? It'll look like that. Then what happens here? Between 5 seconds and 7 seconds, I'm at a velocity of 0. So that means I'm not moving. What would that mean about displacement? Well, if I'm not moving, my displacement's not changing. I'm stuck in that position. So if I'm at 5 meters, which is what this is telling me I am, it's just going to stay at 5 meters for those last 2 seconds. And that's what the XT graph looks like for this one. Okay? One more set of graphs. Now, how is this one different than the last one? Well, I don't see just straight lines on this one. Although I do see some straight lines. So if I look at the first one, I see a straight horizontal line here on the displacement versus time graph. What does a horizontal line on the displacement graph means? Well, it means my position stayed at 1 meter for those 3 seconds right there. If it stayed at 1 meter, that means I must not have been moving. So what would that mean about my velocity for those first 3 seconds? Well, the fact is my velocity for those first 3 seconds must be 0. I wasn't moving because I didn't have a change in my displacement. All right, no change in displacement here means no velocity here. All right, now what I'm going to do is I'm going to do this one right here, and then we'll leave this one for the end. Now, this, I knew this was at rest. Horizontal, straight line. Okay, this one, is it at rest? Well, I can see that my displacement went from 3 to 3 to 4 to 5 to 6, all the way up to 7 during this period of time. This was definitely not at rest. It is constant, though, because it's a straight line. So this is constant velocity. How can I figure out what that velocity is? I do it just like we did on the first one. Delta x over delta t. What was delta x? What was my change in that position? Well, I went from 3 up to 7. So what would my change be? Well, 7 minus 3, the final position minus the initial position is 4. So this would be positive 4 meters. Ran myself out of space again. How long did it take? Well, it went from 5 to 7. So the change in time was just 2 seconds. So 4 divided by 2, right here I have a velocity then. 4 divided by 2 is 2 meters per second. So I know that my final velocity is going to be 2 meters per second, and it's constant. That slope is the same. So this is going to be a horizontal line that goes right like so. Okay? So let's talk about this. It's not a straight line, which means it's not constant velocity. It's a changing. That velocity is changing all the time. Well, we have a name for that. What do we call changing velocity? When you get a velocity change, we went from basically this position where we weren't moving to this new position. That requires a change in velocity. We didn't have any here, but now we do. That's called acceleration. So again, with the lines, you guys, you should recognize we got 3 different types here. On an x versus t, if it's horizontal, all right, a horizontal line on the x versus t, straight line horizontal, it's at rest. If you have a straight line, but it's at some angle, that's a constant velocity. So you have a velocity there. You didn't have a velocity here. And then finally, if it's curved, on the x versus t, a curved line means you got some acceleration going on. Well, the question is, what is the acceleration? We have a pretty easy formula, folks, for acceleration. We know that acceleration equals the change in velocity over time. Well, let's get the time. That's probably the easy one. So to get the time here, actually, now that I think about it, I don't need to know what the time is or even what the acceleration is. We could calculate it, but we don't really need to in this case. We know we started at a velocity of 0, right? The velocity right here was 0 meters per second. What was the velocity when we got to this point? Well, we already figured out what that is. That's 2 meters per second. This here is 0 meters per second. So I just need a line that goes from 0 to 2. I'm just connecting those two. That's what your graph's going to look like for this one. Okay? Again, horizontal at 0 when I'm at rest. We have to figure out what the velocity here is for this straight line that's here. That's what that is. And then when I get a curved section, I'm going to get an angled line on the velocity. And I just pretty much connect the dots. If I know what this velocity is and I know what this velocity is, then the line that represents this part is just going to connect those two. That's all. Okay. What about this? At rest, constant velocity or acceleration? This one is not horizontal. It is a straight line. That means this is constant velocity. Ditto over here, okay? Constant velocity here because it's a straight line. What about this segment here? This is accelerated. So I'm going to leave the accelerated until the end, because on the last example, we just kind of connected the dots with our change in velocity there. So this is a constant velocity. I'm going to use v equals delta x over delta t. So what was my change in position? Well, I went from 1 to 3. That means a positive 2 meter change. How long did it take? We went from 0 seconds to 2 seconds. That's 2 seconds then. So again, very rough math. This is 1 meter per second is my velocity during those first 2 seconds. I'm going to find positive 1 meter per second and be right here. Remember, this is v versus t. So this is meters per second right here. And we were at 1 meter per second for the first 2 seconds. So it's just going to be a line, nice horizontal line that does this. Okay. We're going to do 6 to 7 here. Now, because it's going downward, I know this is going to be negative. So we'll say v equals delta x over delta t. How much did your delta x change in going from here to here? Well, I dropped down from 3 meters to 2 meters. So that's a negative 1 meter change. Okay? We dropped down, going from here to here, we dropped down, and then it took 1 second. All right? So the time is just 1 second. Well, this is very easy to simplify. What's my velocity at the end? It's negative 1 meter per second. Negative 1 meter per second. Okay? Now, I really can't fill that in. I do know that it's negative 1. Actually, I can fill it in. Negative 1 meter per second then is right here. So it would just be a line that goes from here to here. Notice I am below 0. I'm at negative 1 because we already figured out that that's what this would be. So what do we know about this period where it's accelerating? Well, we know it started at positive 1. That's what the velocity was here. Positive 1 meter per second. And it ended, there's your positive 1 right there. It ended at negative 1 meter per second. So it's simply a line that goes from here to here. Positive 1 meter per second and goes down to negative 1 meter per second. That's what your line's going to look like. 2 left. Again, I'm going to leave the curve for the end. Let's look at these two. I know that this is horizontal and it's a straight line. You're at rest. If you don't get that yet, you need to go back and review this sum. This one is not horizontal, but it is a straight line, which means it's not at rest. It has constant velocity. All right. The speed for the at-rest period is a piece of cake. If it's at rest, it has no speed, so v equals 0 is what we would say. And that means that from 4 seconds, where that line starts, to 7 seconds, we don't have any velocity at all. I can go ahead and fill that in between 4 and 7. I'm just going to put a line right across, right on the 0 line. Okay. For these first ones, we got to figure out what this is. That's a v equals delta x over delta t. The change in position over the change in time. The time's easy. Looks like we had 1 second here. So this is going to be 1 second on the bottom. How much did the position change? Well, we went from 0 to positive 3. So we had a positive 3 meter change. So it's 3 divided by 1, or 3 meters per second. So I know that for this first second, I'm going to go all the way up to here, and I'm going to label this as 3 meters per second for this period of time. All right, so what happened during this accelerated period? What happened during this period? Well, my velocity changed from 3 meters per second to 0 meters per second, or went from here right down to there. Okay, from 3 meters per second down to 0 meters per second in 3 seconds. All right, that's your graph for this next one. Okay, and the final one. Again, I've got a straight segment here. Positive or negative? This one's going to be negative. When it slopes that way, it's negative. This one's going to be positive, however. Let's go ahead and figure these out. They're not at rest. We know this is a constant, both of them are constant velocities, okay? So we're going to use the old v equals delta x over delta t. So if I look at this one, how much did my delta x change? Well, I went from 5 all the way down to 1. So 5 down to 1, that's a negative 4 meter change. How long did it take? It took 2 seconds. So my speed here, my velocity during this period of time is negative 4 divided by 2, or negative 2 meters per second. Okay. How about this one? What's my delta x here? Well, I went from 1 all the way up to 7. All right, that's at 7, that's at 1. We went up that much. That's positive 6 meters. How long did it take? Well, it took from 4 seconds to 7 seconds, or 3 seconds. So my velocity for this one then would be positive 2 meters per second. Okay, so I know this one's positive 2, that one's negative 2. We can go ahead and fill them in down here. So between 0 and 2 seconds, we had a speed of negative 2. So I can go ahead and fill that in. There's my negative 2 right there. I did it for 2 seconds. Then from time 4 through 7, we had a positive 2. So from 4, there's 4 seconds, all the way to 7 seconds, we're going to be at positive 2. And I know the acceleration, I basically went from negative 2 to positive 2. So I simply have to connect these two lines, knowing I was going negative 2 here, and I must have been going positive 2 here. So I just connect the two dots. There it is. All right, so for regular physics, that's all you guys are really going to do here. AP, I'm going to go over just a wee bit more, okay? Just a little bit more. So we're going to look at another example. And this just kind of goes a little bit further with a couple of these questions. So this asks, during which interval is it moving with negative, in the negative direction? Okay. Now, we're treating this direction as positive, that direction is negative. So if you think about it, let's think about the different sections of this, okay? If I look at this, am I going to be moving during this period? Well, my velocity is 0 at this period. So at this period, I haven't moved at all. What about here? Well, I could also say, am I moving here? I am moving here. I'm moving negatively, okay? I'm moving at -2 meters per second. So I know I'm moving in the negative direction here. But what about this segment? Well, this represents, if this is velocity versus time, this right here is an acceleration. And it will be a negative acceleration because I went from 0 to -2. So what I would say here is the interval, again, intervals are time, the interval in which I'm moving in the negative direction, it's both of these. I'm moving negatively here, and I'm also moving negatively here. The only difference is I have acceleration. I'm accelerating in the negative direction here, and during the 5 seconds to 7 second period, I'm moving at constant negative velocity. All right, but in both cases, I'm moving in the negative direction. So this would be 4 seconds to 7 seconds. All right, that's the interval in which you're moving in the negative direction. So what is the total displacement represented in this graph? Now this is kind of a little bit of a trick. If I look at the velocity formula, looks like this, and this was in the video that you guys watched. Hopefully you watched it. It was the extra part for AP Physics. What this is asking for is total displacement. All right. Now, to get total displacement, if I think about which variable this is delta x. How can I solve this simple equation for delta x? Well, I just multiply both sides by delta t. So I could say that delta x, the thing they're asking me for, equals velocity times time. Now, think about what we have in this graph. We have velocity and time. And so when you're multiplying the two axes together, time and velocity, like this, what we really want to do is just figure out what area do we have. Remember, we get area by length times width. So if we can figure out what this area is right here, if we can figure out what that area is, we will know what this displacement is. Now you might say, well, golly, it's kind of a weird shape, but I can break this down into two shapes. All right, I can break it down into a triangle and break it down into a square. And if I just figure out those two areas separately and then add them together, I'll have my displacement. So if I think about what this area is, this is 2 seconds of time and -2 meters or meters per second of velocity. So I'm going to break this up. I'll call this delta x1, and then we're going to have a delta x2 also. But what this is basically going to be is simply -2 meters per second times the time that passed. So I had 2 seconds of time and -2 meters per second of velocity. Now, if you look at what happens unit-wise, this seconds cancels out that second. And so I'm left with meters. So well, that's perfect because I want displacement and it would be measured in meters. So I would say then that this first displacement from just this part would be -2 times 2 or -4 meters. Now I'm going to figure out that little triangle. So we'll call this the second portion of the displacement, or delta x2. And because this is a triangle, we're going to go with 1/2 base times height. So what's my base of this triangle? Well, I would think this is kind of upside down. So my base here is going to be -2. That's, sorry, no. If I say that this is the base, this should be 1 second. And seconds are never negative. All right. That's 1 second. I don't know. It really doesn't look like it, but that is 1 second is what that is. That's what this is here. And then my height here is -2 meters per second. All right, so we can simplify this. 1 times -2 is -2 times 1/2 is -1. And again, seconds cancel seconds, so I'm left with meters. All I have to do now then to get that delta x is add those two together. And so I'm going to get a delta x of -5 meters. Okay. So those are your answers for these two questions. One more and we're done. What is the significance of the point at 6 seconds? So here's 6 seconds right here. Okay, it asks us that. And then it also asks, what is the total displacement represented by this graph? Now, you should have a clue on how we're going to do this one. But the first question they ask us is, what is the point, significance of the point at 6 seconds? Notice what this graph is graphing. It's got velocity on this axis, meters per second. It's got time in seconds over here. Okay? Well, what was your velocity at this moment? At 6 seconds, what was your velocity at that moment? Your velocity would be 0. So think about what's happening here. My velocity started off at +4 meters per second, and it's slowing down, right? Velocity slowing down here. At this point, it goes to 0, and then if it continues, it becomes negative. Can you think of another example where something does that? Where it has a positive velocity that gets slower and slower and slower, and then changes to a negative velocity? I can think of a spot, and that's if I take a ball and I throw that ball upward, and then it comes downward. Is there a point at which that velocity is 0 in the flight of this ball? There is. It's right at the peak. Okay, it's going positive velocity, but it's getting slower, 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 just like we had here. Okay, then you hit 0, and then as it starts back down, you get a negative velocity. It's going downward, but it's increasing. It's getting more and more and more negative, just like this is. If I had to guess, I would guess this is a graph of someone throwing something in the air. All right, at least for this portion of it. So what I would basically say the significance of the point at 6 seconds is, I'd say at 6 seconds, the object turns around. Hopefully that makes sense to you. Now remember, this is not a position graph. This is a velocity graph. And I know when I go from positive to negative, because what sign a velocity is tells you what direction it's in. It means you were going one direction here, albeit slowing down, but you were going one direction here and the opposite direction here where it becomes negative. So at 6 seconds, the object turns around. Okay, easy peasy, right? Okay, so this one, this asks us what the total displacement is. Now, again, we got the same type of graph here. This is velocity versus time. And we already know that I can get a displacement by multiplying velocity times time, or getting the area that's underneath the graph. And so here's what we got to do. We got two sections here we need to deal with, because I've got an area that's under the graph here, but I also have an area that's under the graph there. So both of these. So I'm going to need to combine them just like we did before. So what I'll say is that delta x1, we'll say that this is delta x1. I can see right away they're both triangles. So this is going to be 1/2 base times height. Or 1/2, if I look at this, the base is here. How big is that? 3. We go from 3. So that'd be 1, 2, 3. 3 seconds. That's the base. So I would say this is going to be 3 seconds. Times the height. What's our height here? We went from 0 all the way up to +4. So our height is +4 meters per second. Remember, we're not measuring a distance here. We're measuring a velocity. So this is fairly easy. 3 times 4 is going to be 12, times 1/2 is 6. Our seconds cancel, and we're left with meters. So I know that this right here represents 6 meters of travel, 6 meters of displacement. Now we do the same thing, delta x2, for this little dinky triangle right here. And it's still a triangle, so it's 1/2 base times height, or 1/2. If we say that this is our base, that would be 1 second, right? So this would be 1 second is our base. And our height here is negative 2. So if I combine these two here, I'm going to get -2 times 1 is -2 times 1/2 is -1. And again, oops, I forgot units on this, sorry. Seconds are going to cancel. That leaves me with meters. One last thing to do, just combine these two. We're going to combine these two. So if I want the total displacement, I'm just going to add these two together. So I'd have 6 meters plus -1 meter. So my displacement here, is going to be +5 meters. That's my answer for that. All right. So that is working with graphs and doing some calculations with graphs. You guys are going to get a brief homework assignment. We're not quite done with this, but we're a good part of the way with this graphing stuff. So I will see you guys next time. Go ahead and do the work on this and then take that quiz that's at the end. We'll see you guys later.